All right, everyone, we had a little bit of homework last night, 538, questions 1 to 10. Any issues with any of those questions, 1 to 10? 538, please. 9B, okay. Any others? Yep. We got 8A, we got 9B. Going once, 10. 8A, 9B, and 10 going once, going twice. All right, that's it. 8A comes first. We want to find the net electrostatic force on charge A. We also want to find it on charge B in question B, but in the end, question A and B are almost the same thing, right? If you can do one, you're likely to be able to do the other one as well. So question 8 says, 3 charges are placed in a line as shown in the diagram below. We've got, this is nice because we have this diagram drawn already. We don't need to draw it and whatever. We just draw the arrows indicating the directions here for our free body diagram. What's the net electrostatic force on charge A? So we're trying to find it on this one this time. Usually we're trying to find the force on the middle one, it seems, but it doesn't really matter. Okay, it's not really any different, except that our distance becomes the tiniest bit more tricky. Might be a good idea to circle the MC there. What's an MC? It's one that we don't see all that often, to be honest, but got to be prepared for it. What's an MC? It's a millicoulomb, 10 to the minus 3 coulombs. So we got to know when we do our calculations that we've got to convert that to kilograms, to coulombs. And we do that by multiplying it by 10 to the minus 3. The net electrostatic force on charge A. Well, B applies a force on A. Which way? A and B are oppositely charged. That means they're going to attract each other. And if A is attracted to B, A is going to be pulled which way? To the right. So we're going to call that FBA. The force of B on A is pulling A to the right. Now, B would be pulled to the left as a result of A, but that's not the question. The question is asking us what happens to A. C is negatively charged. A is negatively charged. That means that they're going to repel each other, right? Negative repels negative. If they repel each other, which way is A going to move as a result of that repulsion? It's going to be pushed to the left. It's pushed away from charge C. The force of C on A is to the left. Now, if we get lucky, then these two forces will be the exact same value, and the net force will be 0. Although I suspect that won't happen. If it does, it's only by coincidence. Let's get the value of FBA now. And then we'll get the value of FCA. FBA is K QA QB over R squared, which is 8.99 times 10 to the 9 times 2.0 times 10 to the minus 3 coulombs. Again, we're dropping the sign of the charge as we always do when we plug it into an equation. Even the electric field equations that we started on Tuesday, we drop the sign of the charge when we plug it in. QB is 3 times 10 to the minus 3 coulombs. And R, the distance, is 2.0 meters. We've got to square that. Anybody have a value for that? You get 13485 newtons. That's a pretty big force. But remember, we're also dealing with pretty big charges. It's not coulombs. It's not as big as one of the charges we had yesterday, but still a millicoulomb is still pretty big. Usually we're in that range of microcoulombs or even nanocoulombs. 13,485. Now let's get the value of FCA. This one's a tiny bit trickier. Not a lot, but a little bit. Again, it's 8.99 times 10 to the 9 times QA, which again is 2 times 10 to the minus 3 coulombs, times QC, which is 2 times 10 to the minus 3 coulombs again. Divided by this time, what's our distance this time? It's 5 meters, right? We've got to add 2 plus 3, giving me 5 meters. Let's get a value for that one now. 1438 0.4 newtons. That's quite a bit smaller than the force of B on A, but if we think about that, we make a prediction ahead of time, it should be, right? First of all, C is a smaller charge than B, so it's going to produce a smaller force than charge B will because it's a smaller charge. But secondly, it's quite a bit further away than B is. The smaller the charge, the further away, the weaker the force is going to be. So those two things combined are going to give me a much weaker force. Now we've got to add these together to find the net force. FCA is going to be a negative value, so we're going to say negative 1438.4 newtons plus 13,485 newtons. We add those together, and we get 34521.6 newtons, or 3.45 times 10 to the 4 newtons. Is that good? Can't remember who asked me for that one, but okay. Paige? Oh, is that right? Oh, okay. Okay. Okay, so 9B is okay? Or at least might be okay? Okay. Thank you. Let's take a look at question number 10 then. Oh, here's a good one. Electrical forces are so strong that the combined electrostatic forces of attraction acting on all the negative electrons and the positive protons in your body could crush you to the thickness thinner than a piece of paper. Why don't you compress? That's a good question. Okay, let's use some logic here, okay? If there's an attractive force that would crush you into a really, really small thing, then there must be something opposite to that, right, to keep you from being crushed. What's opposite to an attractive force? Sorry? A negative force? A repulsive force, yeah. A repulsive force. Well, where's the repulsive force? What repels? Negative doesn't repel positive, so the protons don't repel the electrons. I'm sorry? Yes, okay, it's another positive. So where's the positives come from? What makes up the positives in your body? Protons? Where are the protons? Wow, we really need to wake up this morning. Hey, where are the protons in the atom? In the nucleus. So what's going on here? Well, you got protons and electrons attracting each other, but you've also got nuclei repelling each other because they're all positively charged. So the reason we don't crush into a piece of paper or something as thin as a piece of paper is because the nuclei are going to repel each other. They're all positively charged, and they can only get so close together until they push each other away. That make sense? All right, let's move on here and spend a few minutes reviewing our electric field stuff that you did on Tuesday when I wasn't here. We know that an electric field is a sphere of influence that surrounds an object with charge, kind of like a gravitational field is a sphere of influence that surrounds an object with mass. A gravitational field is always going to point towards the producer. It's always going to point towards the mass. This is the Earth. The gravitational field points towards the Earth. Or if it's the moon, or even something as small as a pen, the gravitational field caused by it points towards it. Why? Well, we arbitrarily define the direction of gravitational field as a direction that a small little test mass will move with placed in the field. So if I put a little object right here, a little rock right here, it's going to fall towards the other mass. It's going to fall towards the Earth or the moon or whatever it's on. And because of that, because it falls towards it, we arbitrarily define the direction of the field as being towards it. Gravitational field always points toward whatever causes it. Let's move to electric fields, though. Electric fields, we have two kinds of producers, unlike gravitational fields. There's only one kind of mass, right? We have two kinds of charges. And since the electric fields are caused by charges, we're going to have fields in two different directions. The shape of the field looks the same as it does for a gravitational field. The direction for one of them is the same as it is for a gravitational field, but for the other one, it's not the same. Can you tell me which one, top one or the bottom one, the positive or the negative, the electric field points towards the producer? The negative, yes. The electric field points toward the negative in the bottom one because we define the direction of the electric field as the way that a positive test charge will move when placed in the field. So there's no positive test charge right there, right now. The field is still pointing toward the negative. That's because if I was to put a negative in there, or a positive in there, I should say, it's going to be attracted to the negative. It's going to fall toward the negative producer. So, again, we arbitrarily define the direction of the field as the way that a positive will move. Therefore, right now, it's going to be toward that negative. Let's look at the top one. If I put a little positive right here in the top one, it's going to move away from it, right? That means that the electric field will point away from this positive producer. Now, if I was to put a negative charge in there, right here, which way would it move? It would move away. Do we change the direction of the electric field now? This charge is moving away from the producer. If I took the positive out and put the negative in, does the electric field now point outward away from this negative producer? No. There can be a negative in there. There can be a million negatives in there. It doesn't matter. We don't define the direction of the field in terms of the way a negative moves. We define it in terms of the way a positive moves. So whether there's a positive there or not, the field is going to point towards it. Whether there's a negative there or not, the field is still going to point toward the negative producer, and similarly, away from the positive producer. Does that make sense? There's a question coming up in your unit test, and it's still a little ways away here, but when you see that unit test, when you get that unit test, there's a question coming up on it where you have an electric field. There's a little bit more context to it than what I'm writing right now, but it's essentially it. You have an electric field pointing one way, and I can't remember whether it's to the right or to the left or up or down, or it doesn't matter. You have an electric field pointing one way, and the question essentially asks you, this electron right here, where's it going to go? What's the answer to that question? Where is that electron going to go? Okay, we don't know what caused this field. Is it a positive over here? Is it a negative over here? Is it both a positive and a negative? I don't know. So how do we know which way that negative test charge moves in that field if we don't even know what caused the field? It's going to move which way, Logan? Good. It's going to move to the left. We know that automatically because positives move with the field. That's the way we define the direction of the field. Negatives will automatically move opposite to the direction of the field, regardless of what's caused the field. Okay, regardless of whether it's a positive or a negative or a combination of the two or whatever. All right, we learned the other day a couple equations that describe electric fields. Okay, the first one kind of goes with our gravitational field equation for a producer. Remember, for gravity, the gravitational field caused by something, we could find it by using G is equal to Gm over R squared. For electric field, it's KQ over R squared. The experiencer equation for the gravitational field is the gravitational force experienced, or felt, divided by the mass of the experiencer. The electric field experienced by an experiencer is going to be the electric force experienced, divided by, not the mass, but the charge. Now we get two charges in here, the top equation and the bottom equation. What's the difference? Or are they the same thing? Good. This is going to be the charge of the producer in coulombs, and this will be the charge of the experiencer in coulombs, whatever feels the field. R is not a radius. It's not a radius of a circle. Or it could be, potentially, but not necessarily. R stands for the distance from the producer to wherever you're trying to find the field strength. So it's a distance which could correspond to a radius, but not necessarily. And F, of course, stands for force, the electric force that's felt by or experienced by that little test charge. Now, one little thing that I want to emphasize here, that since I wasn't here on Tuesday, didn't have the opportunity to emphasize, It's so important to put this little symbol above the E. Not because you're going to get marked wrong if you don't put it, because the reality is most of your testing is multiple choice, and certainly your diploma exam is multiple choice, and nobody's going to see your work for that. You will have some written response tests for me, but that's not why I want you to put it. I want you to put that little vector sign over it so that A, you remember that the electric field is a vector field, there is a direction associated with it, but more importantly, so that you distinguish electric field from energy. Okay, at this point, you're probably thinking in your mind, there's no way I'm going to mix up EP is equal to mgh or EK is equal to 1/2 mv squared with one of these equations. Trust me, you will. If you consistently don't put that vector sign over it, at some point you will mix them up this year. I guarantee it. Every single one of you. You might still mix them up, even if you put the vector sign over it. But you're a lot less likely to if you remind yourself that this is a vector and, of course, energy is a scalar. If you're lucky, you're going to make that mistake on a homework question. If you're unlucky, you're going to make that mistake on a unit test or a diploma exam. All right. I want to take a look at an example problem here. We already did 11.1 the other day, and you guys said it went well. So let's take a look at another one here, 11.2 today. It says, determine the electric field at position P that's 2.20 times 10 to the negative 2 meters from the center of a negative point charge, 1.7 times 10 to the negative 6 coulombs. For me in this question, we got to identify givens. For me in this question, it's probably just as easy to identify those givens in the form of a picture. We get a negative point charge here that is 1.7 times 10 to the negative 6 coulombs, 1.6 microcoulombs. We're trying to find the field strength over here at point P that's 2.20 times 10 to the negative 2 meters away. Can you tell me that point P, whatever that is that producing the field or is that experiencing the field? Is there anything there? Okay, we don't know whether point P is producing anything because we don't even know that there's anything there. Right? It's a point. What do we know information about? It's not point P. We know information about this thing, right? That's where all the information is. Is that a producer or experiencer? Is that causing the field or is it feeling the field? It's causing it. Yeah, it's a producer. Now, if there was a charge right here at point P, it would be experiencing the field. If we had information about the experiencer, then we could use the experiencer equation. But we don't. We do have information about the producer, so let's use the producer equation. In the end here, let's use the equation. They're both valid. Okay, they're both perfectly valid. Let's use the equation that we know more about. Do we know more about the producer or this thing that might have an experiencer there or might not? We know more about the producer. So let's use the producer equation. E is equal to KQ over R squared. Be careful when you're doing the squaring of that bottom number. It's a good idea to use brackets with that, right? Just like I have on the board there. Just noticed a mistake here. What's that charge? What's Q? It's not 2.20, right? It's 1.7 times 10 to the minus 6. Thanks for pointing that out to me. We do the math on this. We get 3.16 times 10 to the 3.16 times 10 to the 7 newtons per coulomb are the units that we use for electric field. 3.16 times 10 to the 7. That's a pretty straightforward question, isn't it? Remember, you got two equations, the one we used, and we also have this one, E is equal to F over Q. They're both perfectly valid. in this question and in the rest of the other questions. The only question is, what do we know more about? The producer rate here, or I don't even want to say the experiencer rate there, because we don't even know if there is an experiencer. Do we know more about this producer with a charge of 1.7 or the possibly non-existent experiencer? Clearly, we know more about the producer, so let's use the producer equation. Okay, if you know enough about both, producer and experiencer, pick one. Doesn't matter which one you use at that point. All right, let's see what you can do with these two questions, please. All right, if we don't have any issues with these, let's try this one. This one kind of looks a little bit familiar to us, but yet not quite. Here we've got two charges, and we're trying to find an electric field midway in between those two charges. This is kind of like those force problems where we had three charges. This time, to find the electric field strength at point P, midway in between A and B, we've got to draw what amounts to almost a free body diagram. It's not a free body diagram, because free body diagrams show forces. And we're not going to try to show forces here. We're trying to show electric fields. But it's like that. It's the same thought process that we go through. Let's pretend for just a second that charge B isn't there. At point P, which way would the field point as a result of charge A? Fields always point which way? Away from point A, yes. The field always points away from the positive producer. It would point towards a negative producer, away from a positive producer. So EA, the electric field caused by A, will be to the right. Now, at point P, there's also going to be a field caused by B. But B is positive as well. And we know that the electric field always points away from positive producers. If B was negative, then the other field would point towards it, right? Towards the negative producer. But it isn't. It's positive, therefore the field caused by B will be to the left, away from charge B. We've got my two directions of fields, just like we did in our force problems where we found the two directions of forces. Now we've got to find the values of those fields, and then we're going to add them up, making sure we take into account signs. Let's say EA. By the way, is charge A, clearly we know more about charge A than we know about point P. There's nothing we know about point P. We don't know if there's an experiencer there or not. Doesn't really matter. We know something about point A, though. Is point A a producer or experiencer? It's causing the field, right? It's producing the field. So is B. They're both producers. So let's say the electric field is KQ over R squared using the producer equation. The distance here is going to be what? Yeah, it's half of that. I heard somebody say half. I heard somebody say 1.65. Yes, it's point P is midway between, so it's going to be 1.65 times 10 to the minus 2. And don't forget to square that. Let's figure out what we get there. I get 4.9532 times 10 to the 7 newtons per coulomb. Now let's do the same thing with EB, the electric field caused by B. It's KQB over R squared. Plug our numbers in there. Exact same numbers, except QB is going to be 2 instead of 1.5. We plug all those numbers in, we get 6.6042 times 10 to the 7 newtons per coulomb. Now, we have to add these up. Just like we added up the forces, EA is going to be a positive value, positive 4.9532 times 10 to the 7 newtons per coulomb, plus EB is going to be a negative value, negative 6.6042 times 10 to the 7. By the way, both of these charges that we plugged into equations were positive. But if they were negative, we would still plug them in as a positive value, right? Because we drop the signs of charge when we plug them into equations. We add these up, we should get 1.65 times 10 to the 7 newtons per coulomb. The electric field strength midway between is 1.65 times 10 to the 7. Is there a point here where the electric field strength would be 0? Could you put point P somewhere where there was no electric field strength in between? It wouldn't be midway, because we already put it midway, right? And we find the field strength isn't 0 there. But is there a point where the field strength would be 0? Yes, there is a point, and it would be closer to A. You're right, Dane. We know that it would be closer to A because that producer is smaller value. So it needs to be closer to A than it does to B to get the same value of EA as EB. Does that make sense? Okay, we're not trying to find that. You guys know somewhere in the back of your mind right now, if we did try to find that point, it would turn into a question that was almost the same as that other question that we did yesterday, right? Which was kind of ugly mathematically. We could do it. We could do it, but it's a hard question. Let's try these ones. 550. There's the picture for us that we needed, 11.9. She's trying to find the field strength in question 1 to the left of charge A. So you're trying to find the field strength over here somewhere, right? Same type of problem as we just did, except you're not trying to find the field strength in between the two charges, but rather to the left of both of them. All right, let's see what you can do with both of those questions, please. Let's take a look at number 2, everyone. It says an electron and a proton are 5.29 times 10 to the negative 11 meters apart in a hydrogen atom. Determine the net electric field at a point midway between the two charges. Your instinct has got to be, when you read this question, it's going to be 0, right? Because the charge of a proton is the same as the charge of an electron. You want to find the field strength midway in between. They're going to cancel each other out. But we're failing to take into account the direction when we just think about it like that. Let's draw it out and let's see what direction the fields caused by the electron and the proton are. Here's my electron. It's negative 1.6 times 10 to the minus 19 coulombs. Here's my proton. It's positive 1.6 times 10 to the minus 19 coulombs. Now, you could have drawn it the other way around. It doesn't really matter here because it doesn't tell you which one's on the left, which one's on the right. The distance between them is 5.29 times 10 to the minus 11 meters. We're trying to find the field strength right here at point X that is midway between them. The field strength caused by the electron. Let's cover up the proton. Pretend the proton's not there. The field strength caused by the electron is going to be toward the electron because the electron is negative. We always have a field pointing towards a negative producer. The field strength caused by the proton is going to be away from the proton. So they both end up being to the left. That's why the fields don't cancel each other out. That's why the answer isn't 0 here. Because the field caused by the proton away from the proton to the left, the field caused by the electron toward the electron also to the left. Let's get the values of those fields. We're going to say the field caused by the electron is kq over r squared. That's 8.99 times 10 to the 9 times the charge of an electron, although we're dropping the sign of it, divided by the distance. What's the distance that we use there? 2.645. It's half of 5.29, right? 2.645 times 10 to the minus 11 meters. We've got to square that. What do we get for the electric field there? I'm going to guess it's going to be 2.055. 2.056 times 10 to the 12 newtons per coulomb. The electric field caused by the proton, because the numbers are exactly the same here, the electric field is also going to be exactly the same. 2.056 times 10 to the 12 newtons per coulomb. Now, how do we get the final answer there? We add them up. Good. We add them up. The net electric field is going to be You can make them both negative because they're to the left, which is usually what I do, make left negative. But since they're both in the same direction, it's okay to make them both positive if you want. 2.056 plus 2.056, we add those together, and we end up getting 4.11 times 10 to the 12 newtons per coulomb. Toward the electron. Notice it doesn't say to the left here. It says towards the electron. Can you tell me why it doesn't say left? Why it says toward the electron? Yep. Right, because we could have drawn it the other way, right? I drew it this way, but if you drew it the other way, it would have been to the right, but it still would have been, anyway, you look at it toward the electron. All right, I would like to do one more example here. Scratch that. Let's not do one more example. Let's instead take a quick look at a couple of multiple choice questions. First one that I want you to do is question 44. And then I'm going to have you do question 46, but we'll do them separately. So 44, respond, please, as multiple choice question number 1, please. 17. All right, we got 20 responses here. 15 people said A, 4 people said D, and 1 person said B. The way we're going to look at this, of course, the answer appears to be A because 3/4 of the people that responded said A. Why would it be A? Well, we've got to look at the electric fields here. Electric fields always point away from positive, and they always point toward the negative. So that means that this has got to be a negative value, and this has got to be a negative value. Does the shape work out here? Sure it does. Shape works, right? Because if we had a positive and a negative, shape would look something like this, right? The field lines would just join up like this. If we have a negative and a negative, then those field lines in between are going to repel each other. We had a few people say D, positive and positive. So the idea, people that said D got the right shape. They recognized that, look, they got to be the same charge, but they got mixed up in terms of which way the field goes. Always goes toward the negative, away from the positive. All right, I'd like you to do one more question as well, please. 46, please. Respond to that as multiple choice question number 1 as well. All right, let's take a look at this now. We had, out of 17 responses, we had 16 people choose B, and we had 1 person choose C. Nobody said the answer was A. Happy to see that. In order for the electric field to be 0 midway between, we'd have to have 2 charges that are the same. Right? If you had 2 positives, you could quite easily get the field canceling out if they were the same value of charges, that is. Okay, we recognized that that wasn't the case. We said somebody that said C toward the top of the page. Who was that? Dane, that was you, wasn't it? I'm not.
It's like a scroll. You should scroll it.
Oh, okay. You accidentally clicked the wrong one. Yeah, that's probably what happened, actually. We'll save that anyways. Most people said B here. It is B towards the left of the page. Why? Well, if we look at point X, midway in between, the field caused by number 1 is going to be toward the negative. The field caused by number 2 is going to be away from the positive. And when we add those up, we don't know what the values are, but when we add those up, we're going to get a value that's to the left. Whatever its value is, it's going to be to the left. Does that make sense? Good. Excellent. All right, your homework for tonight is page 553. And you have questions 1 and 3 to 9 for homework. 1, 3 through 9. So basically, up to number 9 except for number 2. And I'm not going to assign number 2 in just a second. Just 1 and 3 through 9. Okay, let's get those done for tomorrow. Unless your Paige, who already has them done, in which case Paige can do 538 for tomorrow. All right, that's it for today, guys.